Hello, I am Karishma Ghadge and I'll be talking about energy harvesting for embedded systems. The topics covered in this survey are as follows. With the increased use of wireless systems at remote locations, it is being difficult to use battery recharging or to frequently supply power in those areas. Hence, we are implementing the techniques of energy harvesting, wherein we are using the abundant energy all around us. This technique of scavenging the energy from the environment is called as energy harvesting. The designing issues for energy harvesting system are as follows. The first and the foremost concern is that to determine which type of source is to be used for harvesting. The first and the foremost is the solar energy, which is available in abundance all around the earth during daytime. It uses the photovoltaic cells which convert the solar energy into electrical energy. Silicon based cells are popularly used. Energy obtained from the pressure, vibration and force is called as piezoelectric energy, and the materials used are called as piezoelectric materials. PZT is most commonly used. Electrostatic energy is based on changing the capacitance of vibration-dependent varactors. Vibration separates the plates of an initially charged varactor, and mechanical energy in this process is converted into electrical energy. Electromagnetic energy is obtained by using the principle of electromagnetic induction, which is the process of generating voltage inside a conductor by changing the magnetic field surrounding it. Using this type of energy, we get improved reliability and reduced mechanical damping, but the devices are bulky. Thermoelectric generators follow the principle of thermoelectricity, which is of creating an electric potential with a temperature difference and vice versa. They work at very high temperature gradients. Considering the fact that when the system is operating, there might not always be sufficient available ambient energy, the most complex decision about designing an energy harvesting system is that concerning the storage of the energy produced. Traditional capacitors support applications that need energy spikes for triggering their operation. Batteries leak less energy than the capacitors and are more appropriate for steady supply of energy operations. Thin film energy storage cells support high number of charging and discharging cells. Fuel cells are electrochemical devices that generate electrical energy by converting the chemical energy without combustion as an intermediate step. They produce moderate amount of power with high efficiency. Supercapacitors are the best option for energy harvesting devices. High storage capacity with handling of high power densities over short intervals of time are the properties of supercapacitors. They can be recharged over a large number of times with high efficiency. One problem with harvesting ambient energy is the wide dynamic range of power which may be below the useful threshold level. To solve this, one of the strategy can be of using multiple sources for harvesting. For example, a single system would implement both solar and wind energy generators. Each used source may not be capable of supplying power to the entire system. Thus, power is discarded, which is known as power fragmentation problem. To solve this problem, power matching switches are used. Maximum power point tracking refers to drawing maximum power from a source at a level that maximizes the power output. If the system is charging at 5 volt, we could charge system when voltage input is greater than 5 volts or for about 5 hours of the day as seen in the figure. The region marked in red in the given graph shows the amount of energy being wasted when the voltage input is less than 5 volts. Now, after using maximum power point tracking, all the power inside the energy curve can be utilized for operations of the system. Thus, when the derivative di by dV of the current voltage curve is equal and opposite to the IV ratio, this gives us the maximum power. Maximum power point is placed into individual modules is done to allow each module to operate at peak efficiency. It is a DC to DC converter enabling system to produce all the power that it is capable of by varying the electrical power operating point of the modules. For the sake of simplicity, let us consider the MPPT techniques that are used for solar energy harvesting systems. The simplest one is the curve fitting technique, which involves calculation of the power and voltage characteristics of a photovoltaic panel and maximizing the characteristics giving the maximum power. The formula for finding this is given. Fractional short circuit current takes into consideration the idea that at any point there exists a single maximum power point that can be calculated by tracking either the current or the voltage. This can be obtained by the current at maximum power is approximately equal to K multiplied by I. In the lookup table technique, maximum power point of the system is calculated beforehand for a particular environmental condition and it is stored. This maximum power point is then set for all the similar instances occurring thereafter. Perturbation and observation technique is most commonly used. It calculates the voltage and current and thus the maximum power at a particular point. Small perturbations of current or voltage is added in a particular direction. If the power increases, then the process of adding this particular perturbation is continued in that direction. If the power reduces, then the perturbation is added in the reverse direction. Many such techniques are used today, with each having its own merits and demerits. For low power energy harvesting, the maximum power point tracking controller that is used should have low power consumption. One of the simplest MPPT techniques for low power is the fractional open circuit voltage. Another technique which is most commonly used is perturbation and observe, which is same as that explained before. One of the important techniques for calculation of maximum power for mismatch conditions and partial shading of the photovoltaic field is distributed maximum power point tracking. Presence of mismatched impacts the power and voltage characteristics and energy productivity can drop down, resulting in more than one maximum power point peaks, making it difficult to determine the absolute one. Distributed maximum power point technique pacifies such a problem. The choice of DC to DC topology, strict size, and operating voltage are considered important for designing such a technique. Adapting a power management strategy that is aware of operating conditions and state of the energy harvesting devices is a crucial issue. Issues related to power management are as follows. A relevant system design where system consumes only as much energy that is produced by a system. Such a mode of operation is called the neutral mode. Such operations raises the possibility of indefinitely long lifetime. Achieving neutrality depends on the factors like power generated and capacity of storage device. Energy neutrality requires to model the power generated by the harvesting transducer and analyzing the requirements of the system. Node-level power management is presenting an algorithm for harvesting aware duty cycling between active and low power modes with the aim of performance or power scaling, with the idea that most of the nodes provide at least one low power mode in which the power consumption is negligible. Methods like dynamic voltage scaling can be used that learns the energy profile of the system at runtime and adapts the power consumption level to match the harvesting energy. Next consideration is of the power management for the whole network. Energy-aware routing protocols and sensor networks typically use battery energy-based routing cost matrices, but only battery awareness is not sufficient to select the best routes. Hence, an enhanced routing cost metric that considers both the harvesting potential of a node as well as its residual battery level is needed. Available power provided and needed by the system changes over time, and the system has to decide which service level to serve with the existing available power in order to provide better quality without wasting any energy. Greedy algorithms and polynomial time algorithms are used to obtain optimal solution. Using these algorithms, a sufficient battery capacity is determined for a system and prediction horizon is developed to reach high performance. Now let us take a look at energy management of these harvesting systems. There exists an uncertainty and fluctuations for the availability of energy. Hence, there is a need to obtain techniques that will ensure that the tasks meet the deadlines and also maintain the maximum quality of service. For meeting the deadlines, the optimization of the scheduling is necessary for better performance. Scheduling evenly distributed workloads allows the dynamic voltage frequency scaling to achieve the lowest energy dissipation. Lazy scheduling algorithm uses late possible policy. Energy DVFS considers a task slack and enables an available energy for determining the pace of operation. Harvesting aware DVFS considers all the tasks in queue and selects one appropriate according to the energy availability. Accurate prediction of future energy is very important. Quality of service parameter can be exploited to adjust the power consumed. Trade-off between scheduling and availability of the energy resources is also necessary. Frameworks developed for the quality of service improvement should consider energy budget management and planning that gives energy consumption at each time interval that decides which tasks are scheduled or dropped. From this survey, we have studied the features for prominent energy harvesting and also the considerations for the system to work at optimum, and have seen this using the maximum power point tracking and the power and energy management. System's lifetime is extended with each energy harvest but has a challenge of maintaining continuous flow of energy and quality, which is also a matter of fact of further research. Thank you.